All right, in this video lesson, we're going to take a look at the work-energy relationship. So in previous days, we've already talked about what is work and how work can change things, how it's a force times our displacement. We talked about energy and how energy can be found in lots of different ways, but we focused on mechanical energy, or basically kinetic energy, the energy of movement, and potential energy, the energy of position, okay? So let's blend those two things together now, because if we are going to do work on things, we know that work has the same label as the label for energy, the joule, so somehow they have to be mathematically related to each other, okay? So let's take a dive into that, all right? So first of all, we call this the work-energy theorem, okay? And what we're saying here is if you are able to apply work or do work on some sort of object, that is going to result in an energy change, okay? So you can't do work on objects without changing the energy in some way, shape, or form. The two primary ways that we change energy is we either speed things up or slow them down, aka a change in velocity, or we change their position. We make them either higher or lower in relative position to the surface or our planet, creating different potential energy, okay? So anytime we do work on an object, we get a change in energy. So we see that on our screen here, that work will equal some sort of change, or that delta means change in energy. Now, this is not very useful for us mathematically because we don't often know the total work, we don't often know the total energy, so we can break it down into smaller pieces. We can say that when we have work, we can either change the kinetic energy, remember this is our moving energy, or it can change our potential energy, which is our energy of position instead. So moving energy, position energy are our two options here, okay? Now, let's take a look at this and think about it, an example of kinetic energy. If I were to have a car and I'm driving down the road and I just stomp on the accelerator, okay, that engine now sucks in a bunch of gas, the pistons fire, and it launches the car forward. Well, we just burned a whole bunch of energy there to make the car move faster, okay? Well, the car is now moving faster, which means we've done work on that car, right? Because we've changed its velocity. So if we can change the velocity of something, that requires work to be done on it, which then changes our kinetic energy, okay? It is no different than if you were a runner, right? If you're going to, work out, right? The term we're going to work out. If I'm going to work out, that means I'm going to put work in to change my velocity, to change my speed, to get faster, okay? Now, you could also put work in to slow things down, right? Because if the work is in the opposite direction of the movement, that work will slow things down. That would be like hitting the brakes on a car, okay? You're driving down the road, you hit the brakes, and now the car is moving to the left, but the work you're putting on that car is going to the right, so your velocity will go in a negative direction, or it'll slow down instead, okay? Same concept with potential energy. If you have a box sitting on the ground and you lift that box up, it takes work to lift that box up, but you are also raising its height. So if you're changing the height of the object, you are now giving it more potential energy, okay? If an apple falls from the tree, okay, it had potential to fall. After it fell, it now is sitting on the ground. It no longer has that potential to fall anymore. So in that scenario, the planet, or gravity, has done work on it to pull it down to the earth and lower its height, which changes its potential energy. So in both cases, work is needed to make a change in energy. Now, as you take a look at this, we see these equations, and you might be thinking, okay, this is not the end, because obviously if work equals change in kinetic energy, we can break it down even farther, okay? So if we know that work equals our change in kinetic energy, we can break this down further, and we can say that work is going to be the kinetic energy final minus the kinetic energy initial, or at the start. Okay? But that even itself is kind of cumbersome. So we're just going to say that the work is equal to kinetic energy little f minus kinetic energy I. Okay? But again, that's still not enough for us. So we can say that the work is, kinetic energy is 1/2 the mass times our velocity squared. And because we're focusing on velocity here as the change, it's going to be the final velocity. And then minus 1/2 the mass velocity squared initial. Okay? So again, we're changing We're doing a change in velocity here to make this happen. Now, this is where you could end it. You could say, okay, I know my work, but work is actually our force times our displacement is equal to the 1/2 mass velocity final squared minus 1/2 mass velocity initial squared, okay? That's getting pretty big, okay? And again, it's lots of things, but if we break it down, we can kind of see how it works. There's one last step to this you don't have to do, but you may find useful at some times. You may find it useful to factor out the 1/2 and the masses. So you may find it useful to say that force times displacement is equal to 1/2 the mass velocity final squared minus velocity initial squared. Okay, so we're just factoring out the 1/2 of the mass because the 1/2 of the mass are not going to change, so you may not want to write it twice in the equation. Okay, so this form of the equation is very useful. So is this form of the equation for us to use. So these are the two I would say are our most useful forms of our equations to use when we're looking at a complete breakdown of this idea dealing with kinetic energy. Okay. Taking that same idea and let's break it down by potential energy now. Okay, so if work also equals a change in potential energy, we'll go a little faster this time. That means our force times our distance is equal to the potential energy final minus the potential energy initial, which means our force times our distance is equal to the mass times acceleration due to gravity times the height final, because we're going to change height here, is going to be our change, minus mass times gravity height initial. Okay, so again, our force times our displacement, or our work, if we want to factor this out, would say that the mass times acceleration due to gravity height final minus height initial would be our form. So these two forms of the equation here again are very useful for us because it allows us to calculate any changes in forces, displacements, masses, and heights when it comes to changing position. Okay, so those are both our two different forms that we can use. Now in your notes, we see it look like this, and turns out comes up into our notes. Okay, but if you've been following along, you already have this written down from the stuff I did on the iPad. All right. Okay, so here's our practice problem. On another run, Justin Jefferson is at top speed 9.03 meters per second. When a silly little corner tries to tackle him, the corner is only able to slow him down to 6.33 meters per second as he runs him over. How much work is done on this in this collision? Okay, so first thing we need to remember is in a previous problem, we knew that Justin Jefferson had a mass of 88.6 kilograms. So we need to pull that information from a previous problem in our notes. And we want to know what work is being done on Justin Jefferson, okay? So we know that he is moving at a velocity of 9.03 meters per second. And then there's some sort of collision. And then afterwards, he's moving at 6.33 meters per second. So some sort of work must have been done on him in the opposite direction to slow him down, okay? So if work is going in the opposite direction, we should expect our work to be negative in our final answer here. Somehow we actually made him move slower than he was moving before, okay? So let's go to our problem. We know that work is equal to the 1/2 mass times velocity final squared minus 1/2 mass velocity initial squared, okay? And we're solving for our work, and we know that his mass is 88.6. We can insert that here. And we can insert that here. And we know our initial velocity was 9. We can insert that here. And we know our final velocity was 6.33. We can insert that here. Okay. A little bit cumbersome to look at, but that's basically what we're going to do. So we know it's 1/2. Now, the mass is 80.6 kilograms. I'm going to factor that out because it's in two places. Okay. And then I'm just going to say, well, I have my velocity final squared minus my velocity initial squared. Okay, so work is equal to the 1/2 times the 88.6. And my velocity final was 6.33 squared minus my velocity initial, which was 9.03 squared. This value here is not, the minus sign does not go with this value. So kind of keep this as its own little entity inside of here. So we don't want to lose that minus sign in our math here, okay? As we do this. If we solve for this, we're going to find out that as Justin Jefferson does this work, that we end up getting a negative 1,840 and work is in joules of work on this, okay? If we go to our screen here, we see that same math, same idea. In this case, we show you it so you don't see how that mass has been factored out. So we have the 1/2 mass. Here is our final velocity squared minus 1/2 mass initial velocity squared. If you prefer to do it this way, it works just the same. The only benefit of doing this way, you probably won't lose that minus like you potentially would have had the way I solved it on the iPad. Okay, so we have a negative 1840 joules, which would make sense. He should be making negative work because if he is moving in a positive direction and we slow him down, the work has to be negative on him. Okay. Now, what happens if that corner drags him for 3.5 meters and then finally lets go? What was the force that the corner was able to generate on Justin Jefferson? Okay, so we know what the work is, and we know work is force times our displacement. So the work is a negative 1840 joules, and we're trying to figure out what that force is, and our displacement was 3.5 meters, okay? Well, we just divide by the 3.5 meters, and we should be able to say that the force acting on him is a negative 530 newtons of force acting on Justin Jefferson in this scenario, okay? So again, that force has to be negative because the force has to be applied into the negative direction. And if we track our negatives through the whole problem, that would be part of the actual math, okay? And conceptually, we should think it through too, because we were slowing him down. And if he was moving in a positive direction, slowing him down should be negative, okay? All right, so that is just one example problem that we can do working through this idea of the work energy theorem. Obviously, there are much more examples that can be done because we could do one that dealt with raising things up or lowering things down, changing the heights, also on here. We will leave that additional practice for Socrative and your homework. Thank you.